this segment we'll begin talking about capacitance. So we need to introduce you to something called a parallel plate capacitor, which is a useful instrument for storing charge as well as a lot of other things. The general idea is, as we've seen before, if you take charge and you take it off, negative charge off of some ball and put it on another ball, then you have the dipole, essentially. It's not an efficient way, though. It's very difficult to get that charge to stay put. It tries to leak off, but we've found a configuration that works quite well for storing charge, and this is it. The general setup, so the basic configuration is like this. We have two plates that are parallel to each other and kind of close. Of course, they can't touch. So, essentially, what we're doing is we're stealing a certain amount of charge, Q, and we're taking that charge basically off of one plate, putting it on the other, and then allowing them to attract to one another. So it should look something like this. So the red is the positive plate and the blue is the negative plate, and they exhibit the same kind of electric field geometry that we saw previously for a single plate, except for we actually get a bit of a double effect out of this. So let's pull one of these to the side here. So let's pull this out a little bit, so that we can kind of see a little bit better what's happening with the electric field. The electric field is now going to look something like this, with positive charge on the positive plate being the originator for the field lines, and negative charge on the negative plate being the receptor for the field lines. But we do remember that the positive charge results in some away lines, and the negative charge results in some receiving lines, meaning that there's a double effect involved here. So that the darker green represents the field lines that are going toward the plate, and the lighter field lines represents the fields that are going away from the positive plate. And what this means is that the field of two plates together in between is actually twice that of the field of a single plate. Remember that the electric field due to a single plate is equal to the charge on the plate divided by 2 times our epsilon naught constant times the area of the plate, or that is for one plate. So when we take the electric field in between a parallel plate capacitor, then we get 2 of those. And if you double this, then essentially what you're saying is you're losing the 2 in the denominator, because there's no longer a 1/2. See, this 2 in the denominator is basically you're taking all of this and you're dividing it by 2. So we don't have to divide it by 2 anymore because we have double, so it cancels that 1/2. And we end up with this instead. Okay? So, when we achieve this, anytime you take charge off one plate and put it on the other, what you're doing is you're establishing a voltage difference between the two plates. You can attach a battery and then control what that voltage is. So if you have a battery and you say, let's put the negative terminal on this side and the positive terminal on this side and connect them to these plates, then this is the configuration that you would end up seeing. So we have an electric field in between the plates, we have a total charge that got moved from one plate to the other, and we have a voltage difference between our plates. The efficiency of a device like this is called the capacitance. The capacitance is a new variable in our unit, and it's given the capital letter C, and has the SI unit, the farad. Now, just the same as we don't really see coulombs, we usually see microcoulombs and nanocoulombs. We actually pretty frequently see microfarad, nanofarad, picofarad. Those are pretty common, right? So, what is capacitance? Well, we're about to introduce another always equation. The definition of capacitance. The definition of capacitance is the amount of charge that can be held on a device per unit voltage. So in other words, if I were to put a 6-volt battery and I get a certain amount of charge on this capacitor, if I were to apply a 12-volt battery, I would get twice as much charge on that capacitor, because the capacitance is basically like the shape of it. It's the bucket size. How much water can you put in a bucket? How much charge can you put in a capacitor given a certain amount of voltage, right? Something worth noting, this Q is not necessarily like the total charge in the circumstance, because if you think about it, the total charge is always going to be 0, right? You take it off of one plate and put it on the other. Q is the amount of charge that was moved. So another thing to think about is that, and I mentioned this before, you are creating a electric field with parallel lines. So this has a constant electric field. So it's actually a very good way to make a constant electric field. Now, because this is a definition of capacitance, it means that anything can have capacitance. Your finger can have capacitance, a house can have capacitance, anything can have capacitance. And this equation means that the capacitance of that object defines how much charge will be stored on it based on the potential that's pushing the charge on. So we have a particular capacitance that's associated with a parallel plate capacitor. So I'm going to label that here in the same way that I took the electric field that is specific to the parallel plate capacitor. We'll list the capacitance that is specific to the parallel plate capacitor, and it's the area of the plates over the distance between the plates. Now this is important to think about, because if you take the area of the plates and you make them larger, then that means that if you put a battery on the plates, then the larger the plates, the more area there is for the charge to reside on. So like if you make the plates really big at 9 volts, then all the charge that you're placing on them goes, oh, wow, we can spread out now, right? And then so that leaves me room for more charge. If you make this plates smaller, then what occurs is you're cramming all that charge together, and as you cram all that charge together, it becomes harder and harder to push charge onto the device, and therefore the capacitance goes down as the area goes down, and the capacitance goes up as the area goes up. Now you can also get an intuitive feel for the distance in the denominator. You've got all this negative charge on this plate. You don't want to go there, right? If you're a negative charge, you don't want to go there with all those other negative charges. But if we move the plate in, then essentially what we're doing is making that negative plate more friendly to you as a negative charge. So if I bring that plate really, really, really close, then you're going to feel like, oh, wow, there's something to actually be attracted toward, not just repelled by. So that is the significance of the distance between the plates. The smaller the distance, the better the capacitance. So that's generally the features of a parallel plate capacitor. Now, if we are to take a look at some numbers, we can go ahead and get a sense of what let's say, a 10 microfarad capacitor would actually accomplish. Okay, so let's take a regular 9-volt battery like you've used in labs. So we'll make this 9 volts, and we'll say that our capacitor is it has an area of, let's make it 0.25 square meters. That's pretty decently big. It's kind of like countertop space. A little bit of small amount of countertop space. That might be around the size of a sink, a tiny sink. All right, so if we have this as an area of each of our plates, remember we're really only considering one plate for our mathematics, right? Because it's not a matter of taking into consideration both the plates and how they feel about the circumstance. It's really about one plate mirroring what's happening to the other plate, just in the reverse charge. The area of one of your plates, the charge on one of your plates, if we have a distance between our plates of, let's put it at 1/5 of a millimeter, so that'll be 0.2 millimeters, which is, so let's go ahead and find out what the capacitance of such a thing would be, okay? Remember, that's a pretty decently sized plate, right? If you take a square meter, this is 1/4 of that, and then you take another plate just like it, and you manage to sandwich them to a very, just 1/5 of a millimeter, which is much thinner than one of your fingernails, right? And we just barely have them separated from each other. Let's find out what kind of capacitance that offers. That's going to give us epsilon naught A over D, which is, that's this equation right there, right? 8.85 times 10 to the negative 12 coulombs squared per newton meter squared. And then we have 0.25 meters squared divided by 2 meters. Okay, and that supplies us with a capacitance, and that should end up with coulomb squared per newton meter, or a farad, right? So in farad, in terms of farad, that provides us 11.1 times 10 to the negative 9 farad, or 11.1 nanofarad, right? Not a lot. So, okay, if we put our 9-volt battery on such a capacitor, notice that we didn't actually need to know what the voltage was. So once we decide to start piling charge on here, we need to apply a battery, and when we do, 9 volts will separate charge until it can't anymore. What charge would that separate? Let's use our definition of capacitance. If we rearrange our equation, we'll find that the charge that gets moved by our 9-volt battery is going to be equal to the capacitance times the voltage across the plates, which gives us 11.1 times 10 to the negative 9 farad times 9 volts, which will provide us with about 100 or maybe closer to 99 nanocoulombs of charge. Okay, so it's actually a little bit difficult to make a capacitor because, as you can see, it's a pretty big one. In other words, you'd take like a yard, another yard of aluminum foil, and you take a sheet of paper to sandwich between them. You could create a capacitor that's very much like this, and this is about what you would get if you took a 9-volt battery and attached it to your pieces of separated aluminum foil. However, in your kit that you will see in your lab, you have 2 capacitors that have far more capacitance than this. We have built a capacitor, a really big one, that is 11 nanofarad here, and the 2 that you have are on the order of 500 microfarad, and they're little tiny things. So we actually are pretty good at making capacitors, Siemens are. Okay, so this is the idea behind a parallel plate capacitor. In the next video, we'll look at some of the goings-on of them and show you what you can do with them.